number 6, and let me first review lecture number 5. And in that, we will keep discussing hardware description languages, the assignment, and then focusing on like testing. Like somebody also asked question about not getting the correct answers, and I explained that let's not worry about getting the correct answer at this point. Just submit the assignment, and then little about design space exploration. Uh, why we need to explore the design space, and the reason is that for every, even for the very basic building blocks, we have different architectures to select from, and your selection depends upon what type of trade-off you are seeking in this complex PPA design space, where you need to whether worry about performance, or power or area. And then I also want to spend some time, little time about learning about LLM, so we understand that how this LLM works and what are the limitations, and then is how to automate testing. And again, coming back to my this basic diagram where I have been just emphasizing that spend more time once you are designing at a high level, and then because once you are at a low level, you have very little space to maneuver or to change things. Uh, so here is the the one part of the assignment which I think everybody should have done it right. I also generated this code and also showed you that how you can generate this code. And then all you have to do is just multiply all the vectors with constant numbers to get this linear predictor. And this was a bit trickier assignment where I generated part of the assignment. I generated this. I showed you how to generate this. I generated the code which would just shift all these values to B, C, D, F, G, and H register, and then showed you how you can actually left this for the assignment for you to uh, generate code for this function, and for this function, for this function, for this function, and for this logic. And I also showed you how to primarily uh, input even WT and KT in the module. So we generated this code, uh, and then we started spending more time on Verilog and saying that we need to understand Verilog so that we can fix if there is a problem. And especially problem would arise once you start seeing a lot of X's, which shows that the simulator is confused. So you got to go back and see what fundamental mistake that you have done. Otherwise, you will have zeros and one, and sometimes Z, which shows high impedance or unconnected. And then we learned about the nets and the register, defining a variable as a wire or a reg, but emphasizing that reg does not mean it is a physical register. Then we learned about how we declare single wire variable, multiple wire, you got to give the range, and then if it is a single bit, you define it like this. If it is a multi-bit, so you say 7 down to 0. If it is a memory, then you say memory is 7 down to 0 means 8-bit memory. But as far as its depth is concerned, you go from 0 to 1024. So it's a 1 kilobyte of memory. So it is 0 up to 1023 is the depth. So that is something how you define a memory. And this is where you have this width of the memory is because it's a byte. So you go from 7 down to 0. So we learned about you can define a constant in decimal, in binary, in octal, in hexadecimal. It's up to you. But preferred is hexadecimal or binary because they truly represent bits and their positions. And then we learned about levels of abstraction. Primarily, there's also switch level. We said we will never get into switch level, but then there's gate level. We are never going to get into gate level netlist. A gate level, but definitely the simulator, the compiler generate gate level netlist. We primarily focus on these two levels. One is the data flow level where we are just using operators, and the behavioral or algorithmic level where we are using uh, high level of abstraction, if else case statement or the procedural blocks. So switch level, gate level, we learned about these. Gate level, we said that it is kind of where you have to lay down your design into gates. And this is the job of the synthesis tool to do that. So gate level is here, data flow is all the operators. So if you are using operators, arithmetic operators, conditional operator, concatenation, replication operators. So we covered all of this, and relational operator, reduction operators, and so we have covered. And reduction means that it will just AND all the bits together, and we don't have any equivalent of this in any kind of programming, high-level programming language. It's more specific to hardware. So bitwise arithmetic operators. And so we have covered all these: equality, inequality, case equality, logical operators, shift operators, and arithmetic shift, where if you're doing arithmetic shift and it's a negative number and you are shifting it by 2, so these three signs. A negative number will remain negative. Once it shifts, it is going to replace these 2 bits which are being shifted out with the sign bit, which is 1 in this case, sign bit. So we'll study this as well. So reduction operator, we have studied this. We have studied continuous assignment, assign, and you use any of the operators. And once you're using assign, this must be a wire. So means this output S and CO, they are of type wire, and wire you don't have to say because this is the default. Default is a wire. So you need not to even define it. Just say these are the inputs and the outputs and the end module. Okay, uh, so this is how you can design a multiplexer. Simplest form of the multiplexer, where you have an assign statement and you say if select is 1, select in 2, otherwise select in 1. So we covered this, and then we said mostly mostly we would like to code in behavioral modeling, where you use high level language constructs. So this code will look like your Python code. You can use for loops, you can use if else statement, you can use while, and but all these statements must come under a procedural block. What is a procedural block? Procedural block is always an always block or an initial block. Initial is not synthesizable, so you must never use it inside your synthesizable code. This can only be used in the stimulus. And because it's a subset of the constructor synthesizable and called RTL Verilog. So we need to, and once you ask code, any Gen AI tool to generate RTL Verilog code, it will ensure that it is only using always statement and not the initial statement. Okay, and because initial is unlike hardware, it only gets executed once, so it makes sense if you are doing behavioral modeling, you have to run several tests and then you have to exit from this. But hardware is more like always, which is always doing something. So always is hardware like, but it's not that you cannot use it in stimulus. You can use it in stimulus as well. How many always block can you put in your code? As many as you want, so there is no limit. So is the case of initial block. So but you got to be careful, because Verilog simulators will can pick any always block and start. So all always block starts at time 0. So this is important. Simulation time 0. If you are not using any delay statement in the code, everything gets executed at time 0. Time 0 finished, no matter how big the code is. From the simulation perspective, everything gets executed at time 0. So if you are looking at the waveform, you will not able to see anything unless there is a clock. So then you see clocks getting low and high, low and high. So there has to be some timing statements to see things at different timing in the simulation. So initial block is non-RTL. This is important and gets only executed once. So it is only used in stimulus. Okay, you can have as many concurrent as you want. You can put delay operator to see things happening at different times. And so once you put delay, your simulator, what it will do is it'll go and start executing other initial blocks. So the job of the simulator to ensure that it should appear to you as all initial and always blocks are getting executed at time zero. Now, so he has to do a lot of management of the variables to get you this feeling, because perhaps the biggest challenge of the simulator is that it is using uh, a processor like a Pentium processor, which is a sequential processor, and it is simulating something where everything is happening everywhere. Okay, so I actually interesting publication and a thesis where I tried making RTL code to be synthesizable and execute on RTL processor. So that's something which we tried, and the student also published his paper. Was an interesting research that we did at some point. So always again is you can use two types of assignment. And this is again a bit confusing those who have not coded Verilog. So there are two types of assignment. One is called blocking. Blocking is this will block execution of this. So first A becomes B, and then A is B. So both are BB. So this is not a swap. Okay, so because this will block the execution of the statement, so these are called blocking procedural assignment. The other one is non-blocking procedural assignment. They happen in parallel, and this is the equality that is used to so non-blocking, B gets to A at the same time A gets to B. So all the statements will happen concurrently at time zero in this case. So time is equal to zero. Why? Because everything happens at time zero. That also, but that happens sequentially. And left hand side must be a register. So these are the example. Whenever you are instantiating combinational logic, either you use sensitivity list, you use comma, but preferably just use this. So this is called the sensitivity list. I think there's something in the background. Okay. Sensitivity list. Oh, it is me. Okay. So there's something which is in the okay. Okay. So there is this dollar time statement. Uh, so uh, and especially this is where if you're using it in the dollar display, you use this. But if you are just putting a delay, you put hash time control statement and statements, and you can have multiple statements where you're doing hash time. And so this is how you use a delay. AB should be delayed by 2 time units, and it goes to C. So this is the delay, and that's how you use delay. I think you can just this goes in. Okay, just making sure. Okay, Ji. So then we had this at, which is a time control. You say at, if something happens here, only then, otherwise, G simulator will come here and wait for this to happen. So this is also for to facilitate simulator to understand when should it go and execute rest of the statement. Otherwise, at is where it is just, for example, pause edge mean if a signal changes from low to high, it gets executed. Neg edge mean if it was one and it gets to zero, and then otherwise it will wait here. Okay. So add clock is same as either it goes to low to high or high to low. So it is a double edge clock, pause edge of clock, edge of clock. So that's how we basically simulate a sequential logic, saying always add pause edge clock, mean whenever clock goes from low to high, and we are in the stimulus will generate a clock like this. So every it will just come here and wait until this event happens, and this event will happen here. And once this event happens, it will do these assignments. And non-blocking will ensure that everything will happen concurrently. And this will also ensure that we are inferring physical registers. So that's code with non-blocking procedural assignment, inferring physical registers. So that's how you are here is also time control, and it only says don't execute it unless there is a change in A or B, because you will get the same answer. So the simulator will not come and execute the statement unless there is a change in a or a B. So sensitivity list जो है is important. Whatever you put in the sensitivity list, uh, the simulator will only execute here. Rest of it, if there is any change in any one. Also, it says pause edge of clock means pause edge of clock like this. Okay. So C goes to C reg, sequential register. So sensitivity list is again important. If you miss anything in the sensitivity list, it has its own consequences. And that's why later version of Verilog would relieve you from this burden of putting everything on the left-hand side in the sensitivity list. A static will suffice, and it by itself simulator will figure out what all left-hand side variables you are using. So I'll put it, replace it with your right hand side variables. If there is any change, it'll come and execute the always block. Okay. So we have already started a resettable register with asynchronous reset, or with active low, mean you are saying if reset go from high to low, and pause reset if reset goes left to high. And usually this is preferred asynchronous. Neg reset is preferred by most of the libraries. So if not reset, register gets 0, and otherwise you assign data to our register. And this is synchronous, where you don't mention it in the sensitivity list. Now you understand, because at is where it will come and stop. So it will only execute no matter what reset is. Okay, if you when you do reset this and bring it back to high, it will not be reset. Why? Because it only comes and sees the reset once there is a clock, and then it sees if reset is asserted low or not. So clock edge and waveforms, then you have to look into the waveform, and you got to make sure that reset is asserted low when a pause edge clock happens. Otherwise, it will not be reset. Your circuit will not be reset. So this is what you have to ensure. If you're doing reset in between, means you assert a reset here and here and here, because the positive edge it will see high, and the next positive edge again it sees high. So it will not be reset. So we prefer doing synchronous resets, asynchronous resets. Like this is an accumulator adding data into a register, something like we also did. So same thing, you have reset 0 and then you add. So that's how you generate, uh, write a asynchronous reset active low or asynchronous reset FT high. You can do one of the two. That's how you generate a clock in the stimulus. You have an initial block. This gets only executed once. So you set clock to 0. So set clock to 0 and assert your reset. So reset is first 0, and after so it's like X. First it is X, because if you don't reset a variable of type reg, it is reset by value X. So after 5 time unit, so 5 time units, so it is basically X. Initially it is X. So this is X value. And after 5 time unit, you assert it 0. And then after 2 time units, you make it go. So it is 5 time units, then 2 time units, and then you assert equal to 1. And then this is how you generate a clock. 10 because it was already to 0, 10 times it is 0, 10 clock, 10 time unit, then 1, then 0, then 1, then 0. So it keeps on doing this because of the statement. So this is a must thing if you are using a stimulus and a synchronous circuit. And because this will never end, so you got to make sure that you finish your simulation also. Otherwise, simulation will never end because of your clock. The clock as keeps happening no matter whether you are giving its input or not, because you have not stopped the circuit will keep on running. It will take the last vectors as the final, and it'll just keep using them to do the calculations. So we have done case X, case Z as well. That it's a priority encoder that you implement. So here is the conditional statement, like if branch, so you have branch address, next address. So it has to come inside an always block, any if, else, else. And if it's a combination logic, you got to ensure that you are assigning uh, to a variable on left hand side in all the cases. You must not miss any case for combinational block. So you have to say what happens if, else if, and there has to be an else, or you must have uh, a default value. So this is where otherwise it will put a latch if it does not really know what to do. For example, here you are saying if select is this, assign this value to A, this value to B, but then you are not telling what should it assign to B. And the synthesis tool will assume that you want it to remember the previous value of B, and it'll put a latch because it's not a sequential circuit. So we must not have a latches, which are memory elements, works without a clock. So this is very bad to have latches in your synchronous circuit design hardware. So the trick is you assign some default, and then you can be don't care, and you only assign something to whatever is required to be assigned, and rest it will just pick the default value and assign default to the other variables. So that's a smart thing is use this static and then assign values to default. Okay, like here you have something as default, and then it's up to you that you are assigning to A and B, and here you are only assigning to A in case of else if statement, and not assigning to output B. So if select is to tick B00, this is the assignment. Else if, and you even don't have an else, so but you don't worry about it because of this. So all conditions to be checked. If you must have a default. So if there are, you are missing some conditions, same is the case with case statement. Either you put all the cases, in every case you must have a default and assign it to all the variables. But if you don't want to do that, just have some default value. So default, as it is written with different colors, showing you the importance of the default. Loop statements, different types of loops. You can have a repeat loop, you can have a while loop, you can have a for loop, and it's again it is in all programming languages. So any one of the loop you can use, and once you are inferring hardware, remember it will have loop will infer multiple instances of the logic in the body of the loop. Okay, it's not like a programming for loop. So it has consequences that it's just going to replicate hardware for whatever you are. And then we have also spent time learning about the port definition, that input ports are always wires, and I use this diagram. So input ports, that this is input to the module, always going to head is always going to be wire. Output outside the module coming to you is always going to be a wire. So in sending input to a module, this you can have the tail can be a reg or a wire, reg or a wire. Okay, if you are using procedural block, then you have to define this variable as a reg, and it's has to be a reg. Otherwise, it could be wire as well. So head is always a wire, tail wire or reg. Wire if continuous assignment is used to assign a value, or reg if procedural assignment is used to assign a value. And this is how you control stimulus. You use $finish, $stop, $display, $monitor. Okay. So this is how you kind of effectively finish. Remember, I told you you must finish your simulation. Otherwise, it's a sequential circuit. It will never end. So finish is important. Stop or pause suspends the simulation and enters interactive mode if your simulator supports that. Display is like print. Wherever there's a display, it will print. Monitor is very important. It is like a display, but active all the time. So whenever there's a change in something that you want to print, it will just go ahead and print. So for example, here is a $monitor statement, which says $time. And this is the list A, B, C in, C out. If there is anything gets changed, the simulator will come here and will print the statement. But the $display will only be printed where you placed it. So it's the code, the sequence comes to a display statement, it will print it. So you can have one monitor statements if you want to, because you can only have one monitor statement, and it can be only one monitor, which can be active at any time. So like this is the code for RTL Verilog code, which implements this simple difference equation, which says input xn is added into the previous output while it is scaled by 0.5, generating a new output every clock cycle. So it has a new input because it's as a register. So you have clock and reset coming into the module and the output. So it's just a simple design where there is an input coming in, and you are saying add this input into the previous output. So previous output is a register. So it is a register which definitely has to be a resettable register. And after adding, you are putting the value in here and sending out this. So the circuit has to be clocked. So if there is a clock, so clock has to come from outside and reset has to come from outside. So this is the equation that you are saying shifted, added into X, and I think it has to be another variable Y. And Y reg is 0, and then you are assigning it to Y. Yeah, so you assign it to Y, then Y assigned to Y reg. And but the only difference is that you should output Y reg instead of Y. But here you are doing this. This is your output Y, which is also fine. It's up to you that what you want to reset. If this is fine, yeah, why is the reset is fine. I think this is the correct code. Okay, so this is how you basically write a stimulus, instantiate this module. And remember, generating clock is equal to 0, generating reset. Remember, this is how I told you to generate a reset, assert. So you have, it is 0, assert, take it to 1, and then set it to 0 for rest, set it to 1 for rest of its life. Because it will go from 0 to 1, gets your circuit gets reset. And then clock is always, you generate always clock is equal to not clock 10 time units. And in an initial, you say $monitor, it will remain active. So don't worry about an initial block that's not never ever going to end. So you can stop it at any time if you want to, and you have to finish it once you are given all the inputs and generate inputs for using a for loop or whatever you want to do. So I'm just generating, adding 1, 1, 1, 1. So kind of a ramp I am generating as an input to this module. And then sometimes you have to look into, remember, this is an X. So after 5 time unit, you are making it equal to 0. And then after 2 time unit, you bring it back. So once you reset right away, so here are you resetting, your value gets reset. All the values, especially your registers, variables will get reset. and then you start with x is equal to 0, so x becomes 0, then this y, you calculate y, this value will go here, one value will go here. That's once you are every pause edge of the clock, you are registering the value. So value gets into the register. So this is y and this is y reg. So that's how you have to look sometime into the waveforms to understand what is happening in your code. And this is an actual from model sim simulator, which would show you the waveform. And we will also learn how to dump your waveform files and look into these waveforms using some of the tools, reset and yreg. So sometimes the hardware designers, they got to get into the waveforms. Preferably, you should not get into these. You must write your test vectors in a way that they can be automatically checked. But for debugging, sometimes you have no other way but to find out what is happening by looking into all the waveforms. Okay. Parameterization, we have learned about this already, parameterize and how you use parameters to instantiate module. So this is the code, and you can dump your read memory into a variable, a two-dimensional variable mem. And then macros like tick def, tick if, so if def, so you can also use which are at compile time, they will look and see what is to be done, like define in C programming. And then we have covered already task. So we know it's a nice code that instead of copying the code multiple times, you put it in a task. And task has to be either inside a procedural block, either it can be in an initial block or an always block. And it can have any behavioral statement, including timing control. And it has its own input, output, in, out, like a module. So it has everything, but it has to be inside an initial or an always block. That's the constraint. So means there is something which says initial and always at pause edge clock. So you're not going to write initial and always inside a task, but then tasks can have other if else statements, case statements, any declaration. So tasks is very handy, especially once we will be writing stimulus, system verilog, then you define classes, and classes as procedures. Procedures are in terms of tasks and functions. So you define task inside a module. This is a task which is just adding these values. And then always block, you are calling this task. Okay, this name is full adder. It has three inputs and two outputs. So three inputs and two outputs. So this is how you reuse the task multiple times inside of for this, and you're using it. So this is how, and because it is in a procedural block, they are to be reg, variable of type reg, because they are always going to be in a procedural block. Functions is a bit different, and we have learned about them as well. They are implementing combinational logic. There's always only one output, which is name of the function. So we have covered this function, and this is also because of variable. So function identifier is also variable of this much width. So you write it like this. So here is a function mux2 to 1, in1, in2, select, assign. So you can use it outside a procedural block as well. So this is how you use a mux outside a procedural block, a function that is assigning value to us with an assign statement. Test benches are important, and because most of people's life they spend in verifying what they have coded. So this is Verilog. If people are facing problem, you will, because it's most painful part of the digital design is verification. Okay, so it will not come easy on you, and that's why I told you that it's a separate profession, that people are just verification engineers, uh, because it is so important that verify, and it is not simple to and and it's more like computer science problem than an RTL problem, because all you have to do is you have these interfaces, which is input and output, and you got to generate somehow all kinds of inputs and you don't want to physically or manually generate all the inputs, and then you have to check hundreds and thousands and billions and millions of outputs, and there is no way for you to physically go and check. So you got to be smart that how can you invoke different type of coverages, because there's a logic which is going to have millions, sometimes billions, and now they're reaching trillion transistor. So you are basically making every transistor to switch from 0 to 1. You would not let any transistor to sit idle once you are testing, and in a manner that all combinations, and you can imagine that all combinations is not even possible if there are a trillion transistor in the hardware. So you got to be smart. Verification is a difficult task for complex designs. So usually what people prefer to do is to make a model, and make a model, focus a lot on model, and sometimes you can buy models of something which are like standard. So you go buy models, and then this is your RTL code. So you have same test going to both of them, and same results you expect. If you're not getting the same results, you compare. If it is false, you log error and go ahead and do all the testing. And sometimes you will not figure out why you are getting an error. So you have to go deep down into the design, and you must have internal signals also coming into the simulator. Into the model should also give you access to some of the internal signals, so that this is called wide box testing, where you are having access to internal. It's not a black box, internal signals which you want to see whether they are not matching. But I think there is also a course which we are offering in case, which is a semester level course on UVM. Um, and here is because of the importance of design verification, uh, and people have come up with this is an IEEE standard, and why it is a standard and how it helps you, because it just provides you with a framework to learn and have your device in here. Then you have your interfaces, and then you have drivers, and then you generate all the sequence for your test, and there's a sequencer through a driver. It through this interface, give inputs to the device under test, brings those back and to the monitor, and then somehow also checking the functional coverage, that how much, as I was mentioning about every transistor switching from 0 to 1, that how good is the coverage. If it is a state machine, you want to see that it just gets you every part of the state machine. So it has to be very smart way of checking the functioning, and the scoreboard, that how many correct answers you are getting. And then you can have these agents, and you can have multiple of these agents, and almost every agent is kind of doing the same, maybe having different, and especially a system on chip like device which has so many different interfaces and logic and processors. It's not definitely easy to test such an animal. So this universal verification modeling uh, is done like this. So you have, and this shows a little bit more, that you have a sequences and sequencer to the driver, it goes to device under test. You have multiple agents, and you have a scoreboard, and this is the environment which is inside your module. So we may spend, I intend to have like 3-4 lectures, like for analog and then for verification. Those of you who want to spend more time on verification can do that in that part of the course. So here comes the design space exploration. Usually PPA means you need to worry about power, performance, and area. Right? So power is becoming more and more important because of the mobile devices. Performance is the frequency, that how fast you can run the design, and area is primarily that how much area your design is taking. So interestingly, now people are exploring, and remember, because you may have to have some ways of exploring the design space, because it looks like this, like your area, your frequency, is like there maybe different design options will have different points in the space, and there is an opportunity for optimization throughout the flow when you are defining the architecture, once you're doing the verification, once you're doing silicon lifecycle management, implementation, sign off, manufacturing. But mostly because we are doing RTL, different RTL implementation will have different positioning in this complex design space where you have power and maximum frequency. So the tools, today's the tools, once you select a technology, they will provide you a good, definitely an exact um, estimate of how much power your chip is going to take, and how fast you can run your designs. And so you basically, if you have a way of generating multiple RTL designs using artificial intelligence, then you can explore, you can move in this design space, and you say, I am willing to trade off this very low frequency design. And as you can see, I am willing to move up, dissipate more power, but run my design. And there again will be some limitation, and say this is the best, the very best you can do. So you say, okay, this is the best, and this is the best from the power perspective, that it will dissipate this much power. So these are perhaps not good designs, but then there is a design envelope, which is pushing the boundaries to the max. So you explore that design space. So so these are some of the work uh, uh, the people have done in having multiple RTL implementation of the same design, and then exploring design space where you have power versus frequency, and also area is important. And sometimes area and routability are like two things that how easy or difficult, because once you're putting more and more and more logic, its routability becomes very difficult. A place and route is such a difficult problem, having almost infinite options, and doing something which has infinite option, finding an optimal is very, very difficult. Even if you're constructing a house and it has like 4 bedrooms and two kitchens and um, a drying dining, and so placing them in space has almost infinite options. So many ways to do that. And that's why the architects are just based on your requirements. They give you the best placement. So you got to find out where which one is the best trade-off for your frequency, power, area, and routability. Okay, so remember, as all are competing design objectives: power, frequency, and area, and you are operating in this design space. So these are the boundaries. You can move your design to have low power, but once you do that, low power means that only these options, and these options is low power, but low in frequency as well. But if you try to increase the performance, then they'll start dissipating more and more power. Similarly, you say, I want to run it at the fastest possible rate, then be ready to have some cooling mechanism. They even dip this whole thing into liquid and uh, liquid coolant to cool these things out. And people are really worried about all this generative AI dissipating humongous amount of power and affecting the environment as well. So, but these are the trade-off. If you want performance, means clock frequency, and then be ready and to have dissipate more power, and so putting more and more logic, then be ready. It becomes a routability issue as well. So you need to know that where you are actually operating. So the limitations are that creating design variants is a high effort task. Obviously, if you have so many RTL, even just now we are doing an assignment, just doing one RTL implementation is so difficult. And if you're tasked to do many, so how are you going to do that? So especially for every variant, you got to do the synthesis, then you got to do the place and route and the timing, power, IR drop analysis. So the number of things that you have to do if you have multiple designs, right? So here comes the example of addition. I just want you why there are like so different design options. One is at the architecture level, we will study, and we are studying dedicated architecture. Then we will study time shared architecture. Then we will study systolic and microcoded and different styles of architectures. But within the architecture, you have like so many ways to even just implement a simple adder. Okay, and that will tell you why there are so many trade-offs in digital design. Adders are sometimes, because adders are so important, many FPGAs, they give you hundreds and thousands of these adders, pre-built adders, and you can just instantiate them. Just writing plus sign in your code, the synthesis tool will find out an adder out of the thousands of these adders and will use them. So they have some very generic um, adders and multipliers. Like this is DSP48 in Vertex. Uh, 4 FPGA has this adder and a multiplier. Our DSP48 unit has these 2 multipliers and 2 adders, and it can be put into so many different configurations. Similarly, Ultra FPGA has these multipliers and adders. But the issue is, if you are using adders and not multipliers, you may end up wasting a complete unit. So Quick Logic FPGA has all these adders, register, multipliers. This is the Versal FPGA has this DSP48 block, which has this adder. So there are like adder and multipliers, and you can again put them into different ways of doing MAC operation, multiply, addition operation mostly. And you can do that using these blocks. So, and you can even do floating point multiplication additions in Versal FPGA. By they have this macros, like they have actually developed the logic around it to give you the functionality of a floating point adder and multiplier. But if you intend to develop one of your own, so here you have to explore the design space, the same design space, that are you willing to spend more area? Then obviously there'll be issue of routability that you will find out. Even just putting a 32-bit adder will have issues of routability, even if you're mapping them on FPGA. Power definitely is going to be an issue, that how fast you can add numbers. Sometimes you can add pipelining into the adders. We will study what pipelining is, but pipeline definitely helps you to increase the frequency, but at the same time, you end up dissipating more power. So frequency and power and area, all these trade-offs are going to be there if you're going to put an adder. So for example, how to infer an adder. So I'll be using all these words, infer and adder. Like synthesis tool would assume that you want to add numbers. Let's say it's a half adder. We know half adder means you are adding only 2 bits, A, B. So there is a sum and a carry. So the 2 bits are being added. You add 1 plus 1. So your sum is 1, your carry is 1. So 2 bits in, 2 bits out. So it's simply you write A plus B, and you say least significant goes to sum and most significant goes to carry. Use an assign statement. So this is a half adder. Then you can also implement it using the gate level primitives. Though there we use data flow modeling, but this is gate level primitives. And it says just ANDing will give you the carry, and XORing will give you the sum. So this is fine. You use XOR and add, and this is a half adder, but we would rather never get into gate level details. If you want to do a full adder, usually we have learned how to make a truth table and then find out the logic for C and S, but no need to do that. You can also instantiate 2 half adders and ORing the two carry bits to get the carry. So this is sometimes, but never ever we are going to get into this level of detail. That two half adder instantiating, that's how you connect them together, and sum and carry. So, but this is the logic of a. But if you look at start looking at different books, logic design books, there's so many different gate level implementations of a full adder. This is one implementation. End of the day, it is taking 3 bits and giving you 2 bits output, 3 bits and 2 bits output. So these are all um full adder. So different full adder. But we would prefer to define a full adder using a data flow modeling, where we say A plus B plus C in, and here is the carry out and sum. So this goes to sum and this goes to carry out. So you have A, B, C in 3 inputs and 2 outputs. Okay, so that's how we define a, a full adder, right? A full adder. So, but the slowest and that takes the minimum area, so you will have minimum routing issue, is called a ripple carry adder. What a ripple carry adder does is that it uses a full adder, a full adder, a full adder, a full adder, a full adder. And because we are always going to generate all these adders using generative AI, just you only need to know. So I'll not spend too much time into getting into the architecture so that you don't worry about how to generate. But if anybody is interested, you can go and look into these in more details. So let's add. This is how we add number. If we are given to add numbers, 0, 1, 1, 1. So this is how we add as a human. Once we are tasked to add numbers, we add them like this. So we add starting from the least significant bit. We add 2 bits together, 1, 1, 0, and we put a carry here. 1, 1, 0, 1 carry. 1, 1, 1, 1, 1, 1 carry. So this is precisely you add a full adder, move the carry to the next bit location, and so rippling the carry. So carry will ripple through this and goes here. So its critical path will be all the full adder delays. And if it is 32-bit adder, it's a 32 full adder delays, and that is a lot of delay. And you're not able to clock this at a higher clock. And pipelining this is also not that trivial. A full adder, a ripple carry adder is not that trivial because you have to just stop all the inputs uh, to for them to be in sequence with uh, rest of the additions happening in the design. But I generated this code using ChatGPT. I asked ChatGPT to generate me a code of ripple carry adder using a for loop. Okay, so very nice that, because I also wanted it to generate a overflow logic, which is a carry out from the second last full adder and the carry out from the last full adder. If you XOR it, it will give you the overflow. If your answer is overflowed for this, so it will show you that your answer is overflowed and here is the logic. But that's how it is adding into ensuring that because remember it will be replicated. A carry I plus 1 next time will be carry I. So it is doing for I is equal to 0, I is less than 6, I is equal to I plus 1. Carry bit is going here, sum I is going here. It is taking bit by bit starting from A0, B0, carry 0. Carry 0 is carry in, and you generate carry 1. Next iteration carry 1 comes here. So this is the carry 1. It is coming here. And next carry 2 going into this. So exactly it is implementing this logic. And so this is a bit slowest adder. And so people have come up with so many different ways to accelerate the process of addition. And again, please remember that two things that I want to do with this. First, tell you that how you are exploring the design space where you can minimize or you put more area, put more silicon, and get better results as far as the performance is concerned, because mostly people are concerned about performance. So Now you start, you say, no, I don't want to put a ripple carry adder. Let me see, explore other adders. So carry select adder is one of those adders. What carry select does is it says, if you observe this, you have to wait for the carry, and only then you can add two values. What if you can somehow uh, uh, pre-cook compute both the answer, carry 0, carry 1, carry 0, carry 1, carry 0, carry 1. So you partition your adder into 4 bit, 4 bit here, 4 bit here, 4 bit here, 4 bit here. Okay, this is A 3 down to 0, B 7 down to 4. This is A and B, A and B, 4 bit adder. And independently add all these 4 bit adders independent of seeing what carry you will get from here. Both possible answer, both possible answer. So end of the day, you will have two answer. One answer is coming from here, which is your assuming carry bit of 0, and another answer coming from here. This is assuming carry bit of 1. And once you get a carry from here, you select the right answer here and also the right carry out. So there still will be a delay, which will be this, and whatever delay is this. Okay. So, but you are doing a lot of things in parallel, and that tells you the trade-off as well, that now you have doubled the amount of the area which otherwise would have been there, more than doubled, because now all these are the ripple carry adders and all these muxes. So you are trading off, putting in more area and doing this. So you have this ad. So I asked Chat GPT to generate me a carry select adder. So 16-bit carry select adder. So it does this for me. A, B 16-bit, C in, sum 16-bit, C out. So I'm happy the module in and outputs are defined. Okay. I'm also happy to see that it has like these for the sum 4-bit sum 1, 4-bit of sum 2, C out and C out of 4-bit, and carry SS 4 bits. So what it is doing is now it has so assuming generating these sums and carries, 4-bit sums and carries, assuming uh, uh, so it is actually like these are two-dimensional. Okay, so these are two-dimensional. So these are two-dimensional. So it has done uh, all these uh, first 4-bit block. This is the so first 4-bit block. This one is here, and you have the carry, and this one is here, and this one is here, and this one is here. So it has all these four blocks. Very nice, very compact code, and you have to be a very good programmer to generate this type of a code. So I'm happy with the code it has generated. And I'll show you the test bank that I wrote to test the design. So nice input output and nice way of catering for the all these blocks. Perhaps will take you at least few days to get to understand and design this, which it has done like in few seconds. And sometimes there's a non-uniform means because of the delay here, because this is the critical path. And you say, I'll have this smaller so that this comes first. And while it is going through the mux, I have this ready, this ready. This is sequentially I add. So people have been experimenting, having first section 3-bit, then 4-bit, then 5-bit, something like this to have it like this. And then people are also trying to do a hierarchical, like instead of having uh, just waiting, further dividing it into two parts, resolving this, and then once you have carry from this, then you pass it to this, the other stage. So hierarchical means that you convert it into hierarchical. This is one, this is two. So you merge these two together, that you have an answer for both of them, and you merge these two together. Once you have an answer for this, then you can select one of the answers of the 8-bit. So you have 4-bit here, 4-bit here. So you have 4-bit of carry select adder. So 4-bit here, 4-bit here, and many of this. So you combine these two first and these two first and have 8-bit carry select adder. Then combine 8, then you have. So then people have another type of adder, which is carry look ahead adder. I said, why not to look ahead for the carry, generate all the carries upfront? And how could you do that? It says generation. The carry is actually either both the bits are 1, so you will always have a carry, or there is a propagation, that if the previous carry comes, then one of the bits is 1, it will be propagated. So either you are generating or you are propagating a carry. So they came up with this logic for the carry, and if you do XOR carry with the propagation, you get the sum. So what they do is, again, I don't want you to get into these complexity, but I want you to know that there are so many different types of adders which you can ask any of these generative AI tools to generate these for you, and you put them in your design and see the design space exploration and see which one is giving you the best result: RTL1, RTL2, RTL3, RTL4. So that is your design space. So here is like carry 1, but if you have carry 1 here and you input this carry 1 here, so you can directly generate carry 2. If you put carry 2 and put it in carry 3, so you generate carry 3 as well and carry 4 as well, and then you can have a group carry, group propagate. So they come up with this, that all the carries can be generated upfront. Carry 1, obviously you're putting more area, but in 2 gate level delays, having bigger and bigger these gates, you can generate all the carries, and then you can, this hierarchically, you have 4-bit adder, which is generating group carry, group propagate, 4-bit and 4-bit and 4-bit, and total 16-bit another. So hierarchically, you can build a carry look ahead adder. So this is the hierarchically, you can just keep doing the same thing, like 4, and then you have 16, then 16, 16, 16, 16, you can have 64. So you can have multiple layers. So 64 with carry look ahead adder will have multiple hierarchical structure that you can use to develop an architecture. Then there is carry look ahead adder, carry skip adder. Okay, you can mix some of the adders, and then you will be amazed to see so many different types of these adders, and with the name of their inventors. Brandkung adder, this is Ledner Fisher parallel prefix adder, this is Koch Stone parallel prefix adder, there's Han Carlson parallel prefix adder, the regular layout of an 8-bit Brandkung adder. So uh, perhaps you will find, like, still people are finding interesting ways of adding numbers, just adding numbers, which is so fundamental to what we learn maybe in class 1. And you will find people still exploring interesting ways, because that's all you do, or you add numbers. So let's just take a